Hi there. Hope you've been having a great start to the new year. So let's get back to talking a little bit more about methods in perturbation theory, and in particular, in the next few videos, let's talk about a new method known as the method of multiple scales. Method of multiple scales, and in fact, this idea was suggested by one of the viewers, so thanks for that. Now, in order to get to what is the method of multiple scales, let's step back a little bit and introduce a few concepts first, and in particular the concept of what a secular term is, and then we'll see how, in order to avoid these secular terms, we need to invoke a new method, which is the method of multiple scales. So let's build up to that in a step-by-step way. So in order to understand what a secular term is, let's look at one of the differential equations which we've already looked at before. But there, and I'll put a link to the video where we sort of worked out this differential equation in detail. So the differential equation that we want to look at to begin with is of the form d2y dt2 plus y equals a forcing function, and let's take the forcing function to be of the form cosine omega t. So this is a second order linear differential equation in the variable y. So y is the dependent variable. Now here we are using t for time, and we'll take time to be the independent variable. And again, we are assuming that this equation has been given to us in some suitably non-dimensionalized form. In addition, there is a forcing function which is cosine omega t, which is a cosine function with a frequency omega, which we leave it to be general for now. So omega can be anything, any sort of real number. And again, this is a linear second order differential equation. Now, so again, we have solved this equation previously, but there we looked at an equation of the form d2y dx2 plus y equals cosine of x or sine of x, an equation of that form. And there x was considered to be a spatial variable, and then we solved this equation using the method of variation of parameters. And in that case, notice that the frequency or the wavelength, since if we are talking in terms of spatial variables, was 1. And here again, omega, there are two cases where mod of omega is either not equal to 1 or when mod of omega is equal to 1. And these two cases have to be considered separately, and in fact, this is the main idea behind what a secular term sort of comes about. So the idea for this video is simply to solve this differential equation and see what role omega plays in the solution of this differential equation, and then we'll sort of talk more about it in future videos. So let's just solve this equation to begin with. Now, one of the things we need to do is, first of all, solve for the so if we have a differential equation subject to a forcing, we know that the complete solution y is of the form of a homogeneous solution plus a particular solution which comes from the forcing function, in this case which happens to be cosine omega t. So the first step is to solve for the homogeneous solution, and that equation we have solved quite a few times. So the homogeneous equation is d2y dt2 plus y equals 0. So it's just obtained from this linear differential equation by setting the forcing equal to 0. And I'll put a link to the videos where we worked out the solution for this. The homogeneous solution for this equation can be written in the form a cosine t, a1 cosine t plus a2 sine of t. So I'll put, I think we've worked it out a couple of times, so I'll put a link to all the videos where we have talked about the solution to this differential equation. And now the idea is to solve for the particular solution. So let's just write down the homogeneous solution at one point, which is a1 cosine t plus a2 sine of t. And now let's look for the particular solution. So the differential equation is d2y dt2 plus y equals cosine omega t. Okay, so one of the ways for solving for the particular solution is again to use the method of variation of parameters. And again, we have solved this equation for the particular case when omega is 1 The only difference being that instead of the variable being time, we had solved it when the variable was x, which was spatial, but the method of solution remains the same. But in this case, so what we'll do is let's solve for the case. Again, let's solve for this equation using the method of variation of parameters. For the case, first for the case when omega is not equal to 1. And we'll see why it's important, why these two cases have to be dealt with separately. So just as a reminder, in the method of variation of parameters, we are looking for a solution, a particular solution, which is of the form some function u1 of time. And then let's just call cosine t as the first homogeneous solution and sine of t as the second homogeneous solution. So the overall homogeneous solution is a superposition of h1 and h2. So both of them are functions of time. So we have h1 t plus, so let's write time specifically, plus u2t h2t. So this is the method of variation of parameters, or just variation of parameters. So we assume, we make an ansatz that this particular solution has the form some function u1 times h1, which happens to be cosine t in this case, and plus u2 times h2, where h2 is sine of t in this case. And we need to solve for u1 and u2. Now, in order to solve for u1 and u2, it turns out that they must satisfy equations of the form that u1 prime h1 prime plus u2 prime h2 prime is equal to the forcing function. So we can just write down this as the forcing function f of t. So u1 prime h1 prime plus u2 prime h2 prime is the forcing function, which happens to be cosine omega t in our case. And the second equation that u1 prime and u2 prime satisfy is that u1 prime h1 plus u2 prime h2 is 0. So this is what is involved in solving for the second order linear differential equation using the method of variation parameters, that we have to solve for the functions u1 and u2 in a way that u1 prime and u2 prime satisfy these two equations, and from there we determine u1 and u2, and then the particular solution is of the form u1 times h1, which is the first homogeneous solution, and u2 times h2, which is the second homogeneous solution. And the overall solution is the homogeneous solution plus the particular solution. Okay, so let's solve for u1 prime and u2 prime using this. So first of all, using this equation, we can eliminate u2 prime and write u2 prime is minus u1 prime h1 divided by h2, and then we substitute this into this equation. So maybe we can get rid of this for now. So when we substitute this into this into the first equation, we find that u1 prime h1 prime and u2 prime is minus u1 prime h1 prime. Then there's a factor h2 prime here. Sorry, u1 prime h1, and then we have an h2 prime divided by h2 equals the forcing function, which is for us cosine omega t. And now let's get rid of both of these. Okay. So from this equation, we can solve for u1 prime, and in particular, u1 prime is equal to cosine omega t times h2 divided by h1 prime h2 minus h1 h2 prime. And if we put in what is h2 and h1 as well, then we know that h2 is cosine t. So this is sine of t. So this is cosine omega t sine of t divided by h1 is cosine t and its derivative is minus of sine t. So this is minus of sine t times h2 is sine t. So this is minus of sine square t minus h1 is cosine t and h2 prime, which is the derivative of sine, is cosine, and so this is cosine square t. And so what we find is that u1 prime is actually minus of cosine omega t sine of t. And now we need to integrate this equation to find out what u1 is. So let's do that. Okay. So we have the differential equation. A first order differential equation du1 dt is minus cosine omega t sine of t. And let's integrate this now. So u1 of t should be the integral of cosine omega t sine t plus some constant if we integrate this with respect to time. So there will be a dt here plus a constant. Okay, so one of the ways of integrating this is to use integration by parts. So let's do that. So in particular, what we can do is we save some space and somehow write this as u1 is minus cosine omega t sine of t dt plus a constant, and we just use integration by parts, and therefore what we'll do is we'll integrate this and differentiate this function. So this gives us minus of the integral of sine of t is minus cosine t times cosine omega t, and then we have minus the integral of sine, which is minus cosine t, and the derivative of cosine omega t, which is minus of sine omega t. So we pick up a plus here and a factor of omega, sine omega t dt plus the constant, and then we repeat the integration by parts on this term. So we have minus cosine t cosine omega t, and then we have minus of omega, and we again integrate cosine t, the integral is sine of t, sine of omega t, minus the integral of cosine of t is again sine of t, and the derivative of sine is omega cosine omega t plus the constant. So we see that after doing an integration by parts twice, we come back to the same function u1, and therefore this overall integral can be written as u1 is, so we have a minus outside and a minus here, so that's a plus cosine t cosine omega t. Then we have again minus and minus will give a plus, so plus of omega sine of t sine of omega t, and then we have a minus. Now notice that u1 has a minus in front of the integral sign, and there's a minus in front of the integral sign here, and there's a minus here. So overall what we'll find is that this is a minus of, there's a minus of, so there's a minus and a minus which gives a plus, and therefore what we find is that overall this is a minus of omega square, or rather a plus of omega square u1. So just to repeat that, so we have minus minus which is plus, but we have a overall minus sign here which is nothing but u1. So we have a plus omega square times u1, and therefore u1 is, so we can take u1 on the other side, so we find that u1, 1 minus omega square u1, 1 minus omega square u1 is actually cosine of t cosine omega t plus omega sine t sine of omega t. So let me get rid of this step. Okay. So if we are to solve for u1, notice that what we have is 1 minus omega squared u1 is equal to cosine t cosine omega t plus omega times sine of t sine of omega t. Now notice that there is a 1 minus omega square here, and this is where the relevance of omega, or rather we need to solve for the cases differently whether omega is 1 or not 1. And notice that this constant is an overall constant, so we should actually eliminate it when we are doing the integration by parts to begin with, because all we are doing for now is just integrating this function first, finding the relevant functional form for this integral, and then I'll just plug in a c1 towards the end. So in order to find u1, we need to divide both sides by 1 minus omega square, which is only possible when omega is not equal to 1. And therefore, what we'll find is that when omega, when mod of omega is not equal to 1, then u1 takes the form cosine t. We can divide both sides by 1 minus omega square. So u1 takes the form cosine t cosine omega t divided by 1 minus omega square plus omega sine t sine of omega t divided by 1 minus omega square plus this overall constant c1. Okay, so this is the form that u1 takes. Right, so now we need to find out what the other coefficient, what the other function u2 is, And again, just as a reminder, we found the relation, the two relations on which the method evaluation parameter rests on is that u1 prime h1 prime plus u2 prime h2 prime is equal to the forcing function f of t, and u1 prime h1 plus u2 prime h2 is 0. And therefore, u2 prime is actually minus of u1 prime h1 divided by h2. But we already know what u1 prime is, because when we had substituted in this equation, we had figured out what u1 prime is. So let's use that to now find out what u2 prime is, and keep a track of what u1 is, which we've already worked out. So let's write u1 somewhere here. So we know u1 is cosine t, cosine omega t divided by 1 minus omega square, plus omega sine of t, sine of omega t divided by 1 minus omega square, plus a constant c1. And just as a reminder from here, u1 prime h1 prime minus u1 prime h1 h2 prime divided by h2 is the forcing function. Okay. So, if you recall, then u1 prime is actually minus cosine omega t sine of t. Therefore, u2 prime is minus u1 prime, which is cosine omega t sine of t, times h1, which is cosine t, divided by h2, which we've defined as sine of t. So this cancels out, and this is nothing but cosine omega t times cosine t. That's u2 prime. And again, we need to integrate this function to find out what u2 is. So let's do that now. So u2 is the integral of cosine omega t, cosine t, plus integral with respect to time dt, so dt, plus some other constant c2. And now we need to find out what is the functional form for this particular integral. So again, we'll use two integration by parts to find that out. And in fact, I didn't do it very properly the first time we were integrating u1, because I just used the same variable u2 for this whole function with the constant and for this integral. So let me do it a little bit carefully this time. So let's define this integral as u2 tilde, or better still, let's just call this I. And we need to find out what I is. So I is, again, we integrate by parts twice. So let's integrate the cosine function and differentiate the cosine t function and differentiate the cosine omega t. So a first integral will give us the integral of cosine t sine of t times cosine omega t minus, and a derivative of cosine omega t will give us an omega times minus of sine omega t, so that we'll pick up a plus sign here, times the integral of cosine is a sine. And then we integrate by parts this again. So we have sine of t, cosine omega t, then plus omega, and now the integral of cosine is a minus, so we'll have a minus cosine t, sine omega t, minus the integral of sine is minus cosine, or let me write it in the next line. So it's minus of the integral of sine is minus cosine t. The derivative of sine is cosine with the omega, so that is cosine omega t dt. Okay. Now notice that this factor is again the I that we want, and so the overall this can be written as sine of t cosine omega t minus omega cosine t sine of omega t. Now there's a minus and there's a minus which gets cancelled to give us a plus omega square I. So again notice we have an I and then we have a plus omega square I, and if we take it on the other side, we'll find that we have something which reads 1 minus omega square I equals sine of t cosine omega t minus omega cosine t sine of omega t. So in order to find out I, we again have to divide by 1 minus omega squared, which is only possible when omega is not equal to 1. So when omega is not equal to 1, we find that I, in this case, is sine of t cosine omega t divided by 1 minus omega squared minus of omega divided by 1 minus omega squared cosine t sine of omega t. And just as a reminder, the u2 that we were solving for is simply I plus a constant c2, and therefore we can just write it down here that u2, the second function, is this plus the constant c2. Great. So we have u1, which is this function, and then we have u2, which is this. And therefore the overall particular solution for this is of the form, so remember that the particular solution is of the form u1 h1 plus u2 h2. So let's multiply u1 with h1, which is cosine t, and u2 with h2, which is sine t, to write down the full particular solution. So the full particular solution is u1 times h1, which is, so you multiply this by cosine of t, so we have cosine square t cosine omega t divided by 1 minus omega square, plus multiply this also with cosine t sine t sine omega t divided by 1 minus omega square, multiply the constant with cosine t, okay, and then multiply u2 with sine of t. So we have, so if you multiply u2 with sine of t, we will have sine square t from the first term cosine omega t divided by 1 minus omega square minus omega sine t cosine t sine of omega t divided by 1 minus omega square plus the constant c2 times sine of t. So this is a pretty long expression, but notice what's happening here. This factor, which is omega cosine t sine of omega t divided by 1 minus omega square, cancels out this factor, which is again omega cosine t sine omega t divided by 1 minus omega square. So this cancels out. These two have the same same sort of common factors here. It's cosine square t cosine omega t divided by 1 minus omega square, and this is sine square t cosine omega t divided by 1 minus omega square. So these can be added because cosine square t plus sine square t is 1. And so overall, the solution that we find, the particular solution to this equation, is in fact simply cosine omega t. So if we add these two, the cos square t plus sine square t will give us a 1, and so it's this plus c1 cosine t plus c2 sine of t. Okay, and therefore the whole overall solution, which is homogeneous plus particular solution, y total, the homogeneous solution is simply again has the same form as these two terms, and we wrote it as a1 cosine t plus a2 sine of t. So we can combine these terms together to write them in terms of new constants, and we can write the overall solution as a cosine t plus b sine t plus cosine omega t divided by 1 minus omega square when mod of omega is not equal to 1. Okay. Now notice what's happening in this particular solution. Now, and again, a and b are two constants, which will come out from the two. Since it's an initial value problem, it will come out from two initial conditions. So, for instance, we've been given y at t equals 0 and its first derivative at t equals 0. We can find out a and b from this particular form of the solution. But notice the most important thing here, which is what happens when omega gets very close to 1. What will happen is that these terms remain bounded. They are just trigonometric functions which are bounded by 1 or by the magnitudes of a and b. However, the denominator here, when omega is approaching 1, becomes very, very large. And what this means is that if the frequency of the external forcing to the system is very close to the frequency of the homogeneous solution of the system, so notice that the frequency of the homogeneous solution is actually omega equals 1. So if the frequency of the driving force is very close to the frequency of the homogeneous solution or the natural frequency of the system tends to draw a lot of energy from the external forcing. and this is what is coming out of this term 1 minus omega square. As omega gets close to 1, this term becomes very, very large and unbounded. And in the limit, and when omega is exactly equal to 1, this solution is no longer correct. And for that, you'll have to sort of redo the integrals that we worked out for u1 and u2. Actually, the integrals are a little simpler and something that we've worked out in a previous video, and I'll put a link to that. In particular, what happens is, so let me just write down this solution here. So the solution for this equation has to be dealt with in two cases. When omega is not equal to 1, the solution is of the form a cosine t plus b sine t plus cosine omega t divided by 1 minus omega square, which is what we worked out just now. And when mod of omega is actually equal to 1, and I'll put a link if you want to just go through the steps that we worked out before, or we just use the same method of variation parameters when omega is 1 to find out what is the solution in that case. The solution turns out to be a cosine t plus b sine t plus half of t sine of t. So this is when omega is 1. And notice what's happening to this term. Now, time again is not bounded. So as time keeps increasing, this term keeps increasing in magnitude. And in the limit that t approaches infinity, y of t also approaches infinity. So the amplitude of the oscillations of the system become unbounded. They grow unboundedly with time. And that is because when omega is exactly equal to 1, the system's natural frequency is said to be in resonance with the frequency at which the system is being driven by the external force. And the system continues to absorb energy from the external force, and therefore the amplitude of oscillations of the system just will simply grow unboundedly. Now, this kind of a term, which grows in an unbounded way, is called a secular term in the solution of this equation. And again, it's arising because of a resonant interaction between some kind of forcing with the natural frequencies of the system. Now, it turns out that when we are solving for certain equations using perturbation methods, such kind of resonant interactions can appear between terms, let's say, of consecutive orders that appear in a perturbation series. So, for instance, what might happen is that the y naught, if you assume a series of the form y naught plus epsilon times y1, then y naught could be a forcing function to the differential equation for y1, and it might happen that the frequency at which y naught is forcing y1 is actually the natural frequency of the differential equation that y1 satisfies. So what's happening is that if your perturbation series appears to be in this form where the terms grow unboundedly, then that's no longer a correct perturbation expansion of the solution. Especially in cases when the energy of the system must remain bounded, which we can show from other ways. In this case, of course, there is an external forcing, so the energy of the system can extract infinite energy from the system and grow unboundedly. But in perturbation series, it might so happen that that's not at all a correct approximation to the solution. And so, method of multiple scales is one method, an extremely powerful method, in fact, to sort of take into account such resonant interactions and actually get rid of them, because they sort of appear as artifacts in some of the cases, which is when we truncate the series to finite order. Now, however, in fact, the method of multiple scales is actually far more general than just something that's used to get rid of such kind of terms. It's actually something that encapsulates both the boundary layer method and the WKB method that we've talked about before. But we'll talk a little bit more about this in the coming videos. So right now I just wanted to introduce this idea of a term which grows unbounded. And the reason we didn't dwell too much about it when we talked about boundary value problems is because there the boundary was spatially limited. The boundaries are there's a limited spatial extent. But when you're talking about a time-dependent problem, this sort of feature becomes even more manifest because time keeps growing. So, so now in the next part of the video, let's take another equation and see how sort of a resonant interaction can appear between terms of consecutive orders in a perturbation expansion, and we'll see that that's in fact a term that grows unboundedly with time is in fact an artifact to that equation, and so we need to find a way to get rid of such kind of terms, and then we start